Good morning. So let's take a look at what people think about the acidity of things. Yes, part three. Okay. That's part three. So there is no part three actually. So this is part two. So yeah, that's okay. It is just like the misnumbering by iPad. So blame Apple for that. So and right now let's take a look at the question. So it is still part two. So yeah, we only have part two for chapter 15 left over, and then for chapter 16 it will be part one, which is in the other module, right? So let's see what people think about the bases, right? So yeah, basically, let's take a look. So it looks like cloudy weather is at least better for some people, right? So it's about like 50-50 split. Well, I guess 75 for sunny weather, and then only so far like 25% for the cloudy weather. So, but yeah, we have some sort of proponents of the cloudy weather. So then lots of people appreciate the balsamic vinegar, actually, which is good news. So, but it's still kind of acidic if you think about it, right? So like next time you like make your choices in the kitchen, so you can think about, okay, like what about the like white vinegar versus balsamic? Are they both acidic or not, right? So one of them is like basic or something like that. So they will all have contain like acid in them actually. So that's like something to think about, and then like will prompt you to think about the properties of the acid in relation to the H plus or the proton, right? So like what do acids do in terms of the proton? So that's the question which you might ask when you think about something mundane as balsamic vinegar, according to a lot of respondents, right? So you can think about its like chemical composition, and then yeah, you will like recall it has acid in it, and then what do acids do, right? Maybe ask yourself this like mini review question. So then next thing, so it's kind of like logical to ask this question because we're talking about what's it called? Acids still today, right? So, but then we're going to switch to amines. So, and then if you recall, amines can be proton acceptors, right? So they are considered bases. So then what do bases do? So people say, okay, so protons are accepted by bases. Okay, that's a good way to say that. So basically bases accept protons. Okay, great. So they're kind of like opposite to the acids. And this is something to keep in mind because we'll be kind of like delving into that in the like near future. All right, so now let's take a look at some things, right? So basically previously what we were looking at is, or was actually the acid behavior, right? So like maybe we have some sort of acid. Let's say it's going to be a carboxylic acid just to follow the suit, right? And then you have some acid like this. So like it will feature its traditional things, right? So we're going to break the OH bond in order to demonstrate its like acidic behavior, right? And then we will show our counter ions, right? So the anion is pretty easy. So it's mostly redrawing, right? So now I'm going to, okay, so I'm going to show this oxygen with a minus charge, and then total of 3 lone pairs at this point, right? So then also H plus or the proton will be generated. So that's number one. So that's like your acidic behavior. So number two, what we're going to look at today as well. So that's going to be just like a preview, so to speak, from the Gen Chem. So hopefully it was, or you remember that from this type of science. So there used to be this compound NH3. So I just saw it the other day in the like 105 labs, for example. So it's like pretty legitimate to like know that, right? And then ask yourself like, I need to know what this compound is. So what they can do, so they can behave as bases, right? And according to your peers, so that have been participating in the question in the Google Classroom, so the bases are supposed to accept the proton, right? So that's how you can show it, right? So now we need to show the products, okay? So what will happen, right? You're going to form the new bond using this lone pair of electrons, right? So to show that, so all you need to do is, okay, yeah, you can do the geometry and everything, right? So that's your NH3, so which is supposed to be kind of like tetrahedral according to like electron group geometry. It's like when you consider all the things containing electrons, such as H, and the lone pair of electrons is also containing electrons, right? So now this lone pair will become a bond, and then you can just show it as such. So just kind of like spread it, so to speak, right? And then this will become the bond. So you can like draw it. So, but then what's going to be attached to this bond, right? So that's going to be the question here. So you have now your balance of the chemical reaction, right? Which also needs to be performed. Bless you. And then, so like now let's maybe think about this real quick in the Google Classroom once again, right? So the question will be now asked. Okay, so question is, what is on the bond, right? So that is the question. So what is supposed to be here? So I'm going to imagine that these are maybe like a red electrons. That seems to be the color red. So and now they make the bond. So nothing crazy. So it used to be just a lone pair, still like 2 electrons, right? So but now it becomes a covalent bond because it still is 2 electrons, right? 2 electrons are required for the covalent bond. So and now you have here your like H's, nitrogen, and now you need to balance it, right? So something is missing, literally like one element, pun intended, is missing here. So, and then we need to like figure out what it is, right? So also, I'm going to start putting down the charges, right? So it used to be charge of 0 on the nitrogen or the entire molecule of the NH3, right? By the way, so you have a charge of +1 on H plus that gets accepted by the base, right? So which is our ammonia. So this is a base. Generally speaking, this is your proton, which becomes accepted. Okay, great. So now what do we have? What's on the bond? Okay, well, lots of effort going on. Thank you for that. So the bond, yes, it is consistent. It contains 2 electrons. Great. So, but then what's on it, right? So what do you attach? So what's the other missing element? It's going to be hydrogen. So people are right. So, and now finally, another question for this like activity of the morning. So to like kickstart in the morning. So let's see another question. So now, what is the charge on nitrogen product? Why, right? So that's that double question right there. So like we have the product nitrogen here, right? So it's going to be your purple nitrogen, let's imagine, right? Purple nitrogen is going to be the product nitrogen. So now what's going to be the charge here, right? So what I'm going to show is that basically something like that, right? So it can be shown from the organic chemistry perspective. So curved arrows are very popular there. So, and then basically it will show that now the pair of electrons will move from being only on nitrogen to being between nitrogen and hydrogen. As you told me, there's supposed to be hydrogen, right? So also, if you think about it, so and count electrons, something like was happening, right? So basically we used to have 3 H's here, right? So like NH3, like that. So let's imagine it was this way, right? So and then you have your electrons, such as you have like 1, 2, 3, 4, 5, right? So 5 electrons on the like nitrogen, like around it on the like outer energy level, Gen1 of the nitrogen atom. So, but now, if you look at the situation, you are going to have less electrons. So we can even put them in the circle like that. So that's your 5 electrons of nitrogen, right? So then here you have less. Just count the dots, right? So it's going to be 4. What's going to be the charge, right? And why does it happen? So what's going on? So maybe I can introduce another color. So let's say this one is green. And now the green is here. So that's just kind of, I said what I said, right? So and maybe this will help with your reasoning as well. So we have responses here. So thank you for that. And then looks like people are pretty much unilateral. And then there is a great response. So it is going to be +1. So that's what everybody says. Great job. And then because it donates an electron. So that's pretty much it. So that's a great thing, right? So that's what happened, right? So, or because it accepted the positive charge. That's another way to think about it. So you will ultimately run into the charge balance, 0 and +1. So has to become like +1, right? On the one and only product. So that's like one way to think about it. So great. So that's one kind of approach. And then also you lose an electron. You used to have neutral charge on nitrogen, right, with 5 electrons. Now it loses 1 electron. This green electron is gone. So consequently, you have to generate the counter charge of +1 on the nitrogen atom. So this plus charge will be on the nitrogen atom. So yeah, well done. So yeah, if you think about this kind of like losing and donating electrons as well, so that's good job. So yeah, basically here, just think about like mathematics, right? So you have something neutral, and then it loses 1 electron. It's going to be 0 minus -1 equals +1, right? So, or you have to have some, maybe used to have something neutral, and somehow it gained maybe like 2 electrons, let's imagine, right? Plus -2 equals -2 charge. So mathematically, it works out like well as well. So just think about this like in 2 ways. So eventually it will like make it to the exam questions, right? So because we need to deal with this like electron stuff, at least in this science. So maybe even beyond, who knows? So now let's continue with our whatever we had here. So I think we finished around this slide perhaps. So let's see. So we were at the esters. Okay, so these are the esters, right? So like Fischer esterification. So yeah, basically just a little bit of the review. So now we are going from acids towards esters, right? So it's good to do that. So because acids, I mean, not acids, but esters are gonna be derivatives of carboxylic acids, right? So we have their synthesis now. That's kind of like the first thing to think about, or the second one after nomenclature of esters. So how are esters made, right? So typically that's the question. So let's say if you are in, I don't know, some kind of like a cancer treatment, oncology, right, field, so which you might be in that as a, like a medical professional. So you'll be, okay, well, like how do we make some sort of like chemotherapy medicine, right? Medical drug. So that's done via synthesis in the chemistry lab. So there is like no way around that, unfortunately. So unless you derive it from some sort of like marine sponge, which can also be done, but it's like typically like very small amounts of like precious stuff you can get from the like nature, right? So that's why it's better to get it in the lab. So that's why we look at the synthesis of esters in particular. So there could be like ester groups in cancer medicines, right? So that's quite possible. So how do we make an ester? So it's going to be like a pretty much like straightforward way, right? So you need to have 2 things, acid and alcohol, right? So previously we were looking at that pattern, right? Just an example reaction that can be applied to many other reactions of this kind. So we must lose the OH from the acid. So, and we must remove the hydrogen H from the alcohol, right? So that's how it goes. So it's a little bit kind of like counterintuitive when we talk about acids, right? But here you need to only focus on this particular reaction, right? In which like it was experimentally determined that the acid will be losing OH, right? So, but I don't say it loses hydroxide or loses like H plus with oxygen, right? I don't say those like words, right? So here it's just OH, combination of atoms, right? So, and the ethanol will lose the H, right? Not H plus, not proton. I never say those words, right? So just kind of like be kind of like safe saying that it's going to be lose H, lose OH, right? So that's like literally all it is. So, and then here you'll be good actually like from the like electron count point of view as well. So if you look at some sort of like esterification, let's get to examples, right? So like maybe you have some sort of acid like this, right? So I'm just gonna draw some random acid. So maybe like this with a cycle. O and H, right? So then it's going to react with some kind of like alcohol. Let's make a phenol, right? Because why not? So it's a good example. So we need to be able to deal with various compounds, and then it will kind of like once more show, will show one more time that literally you just need to use example reaction, and then it will work in this random example, right? So with the acid and with some random alcohol. So I'm going to eliminate OH from here and hydrogen from there, right? So then you will kind of like notice that technically this bond is broken between carbon oxygen, and you have this kind of like liberated or like free electron available now, right? So then you will have the same situation here. OH bond is broken, and then you will have this like green electron free on the oxygen of the alcohol. So now you just need to connect them, and then you will make a new bond, and then you need to attach like the stuff which is going to be like on this bond, right? So I'm going to show the conditions, so which will say that, okay, well, it's going to be a reversible process. You are going to use H2SO4 as your catalyst, right? So basically it makes the reaction go faster. So it will be like done in like minutes instead of potentially like hours, right? If you use no catalyst. So that's what catalysts do. They accelerate the rate of the chemical reaction. So and now we're going to notice, okay, well, carbonyl with its green electron will be like here, right? So then I will position oxygen with the green electron as well. So I will just kind of like remove this and that part, right? And then I'll kind of connect what is not crossed. So that's kind of like how I can think about it. So now we have this like pentagon here, so that one, and now finally we are making the bond, right? So that's your ester. So done. So then you can do it literally with like any acid that you have, right? Or any alcohol. So except there are some kind of like exceptions, of course, right? We'll need to be mindful of. So, and we'll be in a good shape. So now, so like basically here we have like example which we just looked at, right? It's very similar. So, and then, yeah, there is like nothing interesting in terms of like what's happening in example A, right? So you are going to have the same situation as on the white sheet of paper, right? So the example 2 will be a little bit different, right? So maybe let's take a look at that. So and see how that works. So again, here you need to be like mindful of how many molecules you have, right? So basically here everything is doubled, right? So and then if you think about it, so you have a one acid, two carboxy groups, two carboxylic groups, and you have two alcohols, right? So what could happen is the following, right? So let's redraw this acid and see how it works, right? So yeah, basically I'm going to show the acid, right? So you'll have like OH, carbonyl carbon. Okay, very good. So the couple of CH2s here, carbonyl carbon again. Oops, so that's bad. And OH, right? So now you have two alcoholic molecules. So here we go, right? So like basically, previously we see that like for each carboxylic acid group, such as in example A, we just need to have one alcohol, right? So here we have two carboxylic groups and we have two alcohols coincidentally. So that's good for us. So let's just kind of like draw them around this acid molecule and see what happens. So that's one, and then the other one will be here, OH, CH2, CH3, right? So now let's eliminate the stuff, right? So this will be gone, and this one. So you kind of eliminate one H2O molecule. Then by the same token, you are going to eliminate another H2O molecule, right? So I basically do the repeat of the action on the left here on the right side. So this is kind of like what will happen. So then I'm going to show the reaction arrow, conditions, H2SO4, right? So then I'm going to kind of like go here and then see what happens. So let's redraw the acid part. So which will be looking like this, right? So I'm going to leave those carbonyls alone. Okay, good. So now what am I gonna make, right? So it's gonna be this bond which will be made, carbon to oxygen, and then carbon to oxygen again. So let's draw that now. Let's see. So we have here on the right side, for example, it's going to be O ethyl, O ethyl. So redraw, right? So then we are going to have on the left side. So that's the left side. As I look at that. So like we are going to have carbon, oxygen, ethyl, right? So carbonyl carbon, then oxygen, kind of close to that, and then ethyl, CH2, CH3. Okay, great. So then I'm going to draw the bonds which were made, right? So let's maybe make them green, for example, just to kind of like be conforming here. So that's the one, and that's another one. So if I check myself, then I will see that I formed kind of a double ester, right? Because I have ester here, and I have the ester here in one molecule. So it's kind of a double ester, right? Or you could say there are two ester functional groups in this molecule. And then if you want to like sound professional, you can just call it maybe some kind of like P1, let's say product one, right? So, and then, yeah, if you're not asked to kind of like call it, name it, right? So then you might as well say P1 and then say, well, since we had two carboxylic acid groups and two molecules of alcohol, we performed two esterification processes, right? And we obtained P1 the way it looks. So yeah, something along those words that which you can use at your like exam explanation, for example, right? So then this one will be, for example, I don't know, some kind of like reactant one, right? So this is going to be reactant two, and this is going to be reactant two. But honestly, you can name this guy, right? So this is just ethanol, two ethanol molecules. These are your R2s. For instance, this is product one, so it's like some sort of ester, double ester. Okay, so now let's see what we have. So maybe we actually have activity number 3, so which is going to be just the practice, essentially, of what we have seen so far today and previous week. So activity 3 is show the esterification reactions, aromatic carboxylic acid and alkyl alcohol. So you are welcome to do that. Now there is a call for that. Okay, so you can go ahead. Let's do that one. So activity 3A and 3B is still going to be up in the air, so you can do that as well. So it's going to be later. So, but for now, we're doing esterification 1. So let's get to that real quick. So activity B is still pending.
Am I doing it on the back of this?
Yes. That is fine, actually. So yeah, that's okay. Yeah, go ahead. All right, so let's see what happens for the esterification. So we have had multiple examples so far. So now it's going to be just up to you to put things together correctly and show some kind of like new acids, new alcohols, right? So that will conform to the activity requirements. So that's it. So we have aromatic acid and the alcohol. And yeah, that's great. Okay, well done. So yeah, you will release the water as a byproduct. Okay, good. So again, feel free to maybe attach some sort of like isopropyl randomly on the carboxylic acid, right? So this will just diversify your structure drawing skills. And now activity B. So this one is alkyl carboxylic acid and aromatic alcohol, right? So that's what we will have. So like who wants to try that? So we have activity B. So that's the penultimate presentation, literally. Try to maybe use your chances to boost the scores, right? So bonus points worked out quite well. Somebody lost 6 points on question 11, but then they came back with 6 points in the question, like the bonus points, right? So that was like pretty good. And then they became like a 90 something, like, oh, it's pretty nice, right? So just FYI. All right, so like we have, somebody was raising the hand. So yeah, let's just go ahead and then do activity B. So I just need to be a little bit faster today. Yeah, so we'll see. So activity B. So now things are flipped. It's alkyl carboxylic acid and aromatic alcohol, right? So like those words are supposed to mean something. And yeah, we just need to see if we agree, kind of like our response agrees with the requirements of the activity. All right, so let's see what we got. Alkyl carboxylic acid. So it's going to be just a carboxylic acid based on some sort of alkene, right? There's going to be nothing aromatic. Okay, that's a good example. So yeah, just like a short chain relative to carboxylic acid, but aromatic alcohol, right? So it has to be, that's an example, right? So again, you can always put some sort of a substituent, right? Whatever it might be on the aromatic ring. So it doesn't kind of like break away from aromaticity, right? So it's just going to be substituted phenol. So, but here it's pretty straightforward. So like this is your ester, right? So like for the conditions, say it is H plus, right? So because it is going to be the proton, not just hydrogen atom, right? That's a big difference, right? So just mind your charges, basically. That's what I want to say. So then that's a byproduct. Okay, well done, awesome. So yeah, these are like our esters. So now let's move on, I guess, to the next points. So it is going to be about acid chlorides and then acid anhydrides. So these are just some more derivatives slash new functional groups to introduce, right? So basically acid anhydride looks like that, right? So that's the combination. So to put it in the words, you have the carbonyl, so which is connected to the oxygen, which is in turn connected to another carbonyl. So that's the acid anhydride. So for the acid chloride, that's what it looks like, right? So that's going to be acid chloride. It's looking like that. So now we're going to look at some kind of like more tangible things, which are going to be just examples, right? And then specifically, we'll get right into the synthesis of those, right? So not the synthesis, but sorry, chemical properties, right? But basically, just to put some things into perspective. So you used to have some sort of acid. Let's say whatever Bryant was showing to us, right? It was something like that, perhaps. Okay, so there was like oxygen here and OH, right? So then you're going to apply like certain chemicals, right? So to make those acid chlorides. So yeah, basically, so we are using sometimes those kind of like chlorinating agents, right? Such as PCl5. It's going to be done at some kind of like elevated temperature. And now what's going to happen is that basically this OH group will be eliminated, right? So, and then you are going to switch it to, guess what, chlorine, right? So, and you're going to get your acid chloride, which is going to be like this. So redraw those carbons, 3. So this is carbonyl here with the oxygen intact. And now here you are going to have your new atom, right? So which is going to be that. So that's it. You just made it, right? So this is going to be like a bonus chemical reaction if you want. So you have, maybe you will have not PCl5, but PBr5. And guess what? Instead of chlorine, you will have bromine here, right? So just kind of like look for this correspondence. So now let's see. So why do we need to care about acid chlorides? Because they apparently can be used in synthesis a lot. So and then we can make esters from them, right? So the reaction that will take place is going to be acid chloride plus alcohol becomes an ester, right? So some particular examples here. Let's take a look, right? So you have your parts from the acid, right? Parts from the alcohol. That's like a good way to think about it, how things are constructed. So like the more approaches you have, the better it will be to kind of like for you to solidify in your mind what the ester is, right? So consider this as an exercise in science and such, whatever, right? So, but then from the general example perspective, I kind of like emphasize it because this can be used for any acid chloride and any alcohol pretty much, right? So you are going to eliminate chlorine apparently from your acid chloride, and then the alcohol will lose H, right? So together, it kind of makes sense to lose that because you're going to create HCl, right, which is going to be the hydrochloric acid. So that's another question that's going to be asked in the Gen Chem Intro to Gen Chem lab, which you took before this course. So yeah, this is going to be certainly a familiar compound. So HCl will be released as a byproduct. So just some more examples of reactions, right? So now this one is about the reaction of anhydride and alcohol, right? So like, why do we need to care about those? Because they will lead us to kind of like esters again, right? So we're going to see those as building blocks in the new ester molecule. But if you take a look at some kind of anhydride, so the way it's going to react is going to be similar, right? So it reacts with alcohol. Alcohol is always loses H, right? So it looks like it's the third reaction in a row where alcohol loses H. So then the anhydride has to lose the RCOO, right, to make an acid as a byproduct, right? So that's the one, that's your byproduct acid. So, and that's it. So the leftover parts will be connected. So this black part here outside the ring, right? So, and this black part here, as you connect them, carbon to oxygen, you are going to make your like generic ester of some sort. So now let's see. So that's like a way to synthesize. So this is going to be like about the synthesis, right? So this is just one approach, apparently. So we can call it like approach number one, right? So, but another one is going to be, again, some sort of chlorinating agent has to be used, right? So that's going to be approach number two. To prove that, so let's just like use some sort of like aromatic carboxylic acid, right? So that's what I was talking about. So maybe we'll have this, let's say isopropyl, because why not, right? And then we have CH2 here, and then our kind of like carboxylic acid, right? So then we are going to add to that this thionyl chloride, SOCl2, right? So here is going to be like a new compound, relatively speaking. So, but the point here, when you see that, right? So hopefully you remember this. It's going to be the cue for us that we are going to make the acid chloride, right? So basically, we are going to eliminate this guy and then switch it to whatever we have here, right? It's going to be chlorine, right? So just switch it to one chlorine atom, and then you'll be in a good shape, right? So now to show the product, so we're going to do lots of redrawings, right? Such as this, okay. I'm going to keep this isopropyl because it cannot just be randomly eliminated somehow, right? So then I'm going to keep this CH2. So lots of people did a good job on exam 3 counting their carbons, right? Some people lost them. So yeah, but looks like we are getting better, hopefully. So now you're going to eliminate OH and then switch it to Cl. That's it. So this is your specific acid chloride in this example number 2, right? So with a different chlorinating agent that adds chlorine to the molecule, right? So that's kind of like your synthesis and example here. You can like that's like more examples here. You can use it as a gift, right? So maybe put it on your wall. You'll become like Hamza. So, and maybe this will be helpful or maybe not. So now this is just some more examples, right? With a shorter chain carboxylic acid, same thing will happen, right? So we're just looking at this like a locus OH is gone, switch to Cl. So now we have acid chloride, right? So you can just call it acid chloride. So if you don't, if you're not asked about nomenclature. So which we are not asked about here. So now let's see what else we have, right? So so these are some like more examples, right? So that we're gonna look at. So let's see what we can do. So in this case, I would say it's gonna make sense to do more examples. Okay, so yeah, here we have some new reactions, right? So these are a little bit jumbled, unfortunately, but I'm gonna just redraw them, right? So let's take a look at like the first reaction here. So you have acid chloride with alcohol, right? So let's see what happens here. So I'm just gonna use what I remember from the past, from just a slide, like a couple slides ago, right? So I'm gonna have like, okay, reaction A, for example, right? So here we go. So this is going to be your acid chloride. So now here I exercise my skills of using the skeletal drawing, right? So I don't explicitly show the carbon in the carbonyl anymore. So you need to like understand, right? Or like remember, know, whatever, that there is a carbon in this point, right? At which I point with my finger. So then I'm going to use the aromatic alcohol, which is going to be looking like this. So that's the aromatic alcohol because it has the aromatic group in it, right? So now we are going to make the stuff, right? So here we are going to eliminate chlorine and H. Basically, you can do it like this, so that's fine as well. So H and Cl will be eliminated, so that will give you the byproduct of HCl. And consequently, the organic product will be created, right? So you have free electron on this carbon, and you will have another free electron on the oxygen too. So next, you are going to put them all together and see what happens, right? So we'll have our structure, which will be redrawn largely. So this, and then we have oxygen with a phenyl group, right? Like that. Okay, great. So now let's take a look. Quick question, see if you follow. All right, so where is this? Damn it. All right, so question. What is missing? So that's literally kind of like the mistake from exam 3. So people were doing something like that, right? Not with this reaction, of course, so because it's still in the past, right? So in the past, we didn't have this reaction, but the mistake was made, right, of the same kind. So just like it was made in this reaction. So what is missing now, right? So that's the question. So this is just the observation, basically, skills of yours. And yeah, so could be exercised here. So like don't kind of like miss things basically, right? So like I'm going to move on to the next reaction in the meantime whilst you think about the previous question. So let's take a look at maybe kind of like this reaction to the bottom, right? On the left side, on the bottom. So we have some sort of carboxylic acid and we have SOCl2, right? So which we just now saw as well. And then this looks like a chlorinating agent, right? So basically we're going to turn this random acid into the acid chloride, right? So let's try to do that. So we have our pentagon ring here. So then we'll have the ethyl like this. And then I'm going to have COOH, right? So there's a carbon here in the center. So then SOCl2 is added, and then we're going to make our product, right? So I'm going to basically like remove this OH and switch it to Cl, right? So that's what will happen. Everything else gets redrawn like so. Okay, so that's your ethyl. So then you have carbonyl carbon, bless you, and chlorine will be here, right? So that's your acid chloride. And now, yeah, you are done pretty much. So what else do we have? So yeah, looks like C was actually the synthesis. So I mean like this B. So now like not, it's not yet finished actually, right? So now we can continue, right? So now let's imagine that this is going to be our next stage reactant to which we are going to add the ethanol, right? HO, CH2, CH3. So that's what is added. So, and now the question is, what's going to happen, right? So that's kind of like next stage, right? So question mark. So if this is now your acid chloride, which will be reacting with alcohol, so we are going to use our generic examples, right? And then eliminate H and Cl. And then we will connect basically carbon and oxygen. So like this, they will be connected. So now let's redraw a lot and see what happens. So we have our pentagon, right? So ethyl is here. So carbonyl stays. Then we have oxygen and ethyl. So I'm just going to use those terms a lot because they are familiar. supposedly, and now you have nothing more than some sort of ester, right? So because you have the ester functional group in your molecule, despite its like complicated structure, right? So that's what we are going to have in this situation. So maybe one more reaction to look at will be anhydrides, right? And then I think we'll be good to carry on to actually the next chapter, right? So let's take a look at this anhydride stuff, right? So it's going to be like reaction C in my numbering. So, but I'm going to look at this like rightmost. Anhydride, CO, carbonyl, oxygen, carbonyl, right? So that's an anhydride signature kind of combination or like function group basically, and the alcohol will react. So let's see what happens there, right? So we are going to have the anhydride, which is looking like this. So that's a carbonyl, oxygen, then carbonyl again, and that's it, right? So that's your anhydride. So then it will react with some sort of interesting alcohol, right? So some people call it a box, right? So well, it does look like a box. Maybe like UPS or something like this, right? So and now we are going to see what happens, right? So yeah, basically in this case, so if we recall the general pattern, we are going to end up with an ester and the what's it called? Carboxylic acid, right? So let's look at this. So the hydrogen will be lost by alcohol. So that's one thing, right? So for the anhydride, we are going to break one of the bonds. So typically we'll be looking at like symmetric anhydrides, because if you can think about like further, right? What if here you have phenyl, right? So, but instead of this phenyl, you can have isopropyl, right? The situation will be a little bit more complicated, right? So, but now symmetry will make things easier in terms of the number of the products in the mixture you are going to obtain, right? So, and then basically you are going to break this bond or that bond. The two parts which will emerge will be the same, right? So I'm going to break this like leftmost bond. And now I'm going to eliminate basically this thing. So what's going to happen next is that red circles will be connected, right? So then the only way to connect them will be to look at the free electrons, right? So green electron is free, and now it's going to be also free green electron on the hydrogen, right? So they will be connected together to make a covalent bond. That's why we were like asking like this question in exam 1, what's a covalent bond? So because it's kind of like transpires everywhere as we go, right? So then we're going to make our stuff. So what are we going to make will be the following, right? So let's take a look at the circle stuff first, right? So I'm going to say I'm going to have this H, then oxygen, carbonyl, right? And so I have just drawn the stuff which was in red, okay? So then I'm going to kind of like show the bond here, and I'll be good, right? So this is going to be our like red part. So essentially, I made nothing more than benzoic acid, if you look at this, right? A carcinogen. So now other things, right? So which are circled, maybe let's circle them in green color, right? So this and that. So those things will be connected. So bless you. Where is the connection point? That's the question, right? So this carbon-oxygen bond is broken, and then you have the free electron on carbon. So this OH bond is broken, and then you have the free electron on the oxygen. So it looks like you are going to make a carbonyl-oxygen bond or an ester, as we will see later. So let's draw them and see what happens. So we're going to have, this is going to be like number 1, so carbonyl, good. So then we'll show the purple electrons. So next, we're going to have the oxygen here, box. Okay, box it is. And the methyl, don't forget the methyl, right? Methyl on the box. So then we have what? Purple oxygen, purple electron on the oxygen. And now if you align them like that, so because you have to kind of put them closer to make the bond, does make sense to kind of draw them like here and there, right? So it's going to be like too far. So you are going to make the new bond, right? Which is going to be this one. So, and now you have just created your ester, right? So it's going to be your complicated looking ester in this like mega green circle. And then you can take this example home with you. So yeah, put it on the wall maybe as a wallpaper. So that could be like nice as a background, right? So, but this is going to be just like an example reaction, right? Which is based on our principle, how the anhydrides react, right, with alcohols, right? It could be like any other anhydride, typically symmetrical for now. So, and some sort of alcohol, doesn't matter like what it looks like. So, yeah, these are our things. Okay, so now let's see. So I think we are going to look at maybe like one more reaction here. It's the hydrolysis process, right? So that's kind of like reverse to the ester formation. So here we're going to go basically backwards, right? So previously we were showing this back and forth arrow when we were doing the esterification. So now it's time to go like backwards, right? So we can start with an ester and then add the water to that in acidic conditions, right? So just like Brian was showing to us, so we also need to have H, but with the plus, right? To show the acidic conditions. So, and then what's going to happen next is that water will be acting as the active reagent here, which will be breaking the bond between carbonyl and oxygen in your ester, right? The single carbon-oxygen bond in ester will be broken. So as a result, you are going to reform your acid, right? And the alcohol, that's it. So that's like actually what happens here, like pretty straightforward as well. If you think about it, why is it straightforward? Because you are going to get your familiar ingredients, so to speak, which are required for the esterification. And then if you try to like go backwards, right? So you will just react your alcohol with acid. So based on the previous knowledge, it's going to be Fischer esterification. And you are going to make the ester, right? So that's basically it. So, but here we just need to be mindful about the conditions. We need to show the water as a reagent, right? So because somebody actually told me, yeah, you're missing the water in your like exam key. So that was a good point. So from the old exams, so like when you do the hydrolysis, water will be kind of necessary to show, right? Because otherwise it's going to be unclear what's happening. So, but hydrolysis, again, from Gen Chem, that's a like special kind of reaction when the water kind of cuts thing, right? According to the Greek language. So, and here you go, right? So here you have it, right? So you have H2O in acidic conditions, which will make the hydrolysis possible. And as a result, the acid will be formed and the alcohol will be formed. So alcohol, it is ROH, right? And then you have RCO and OH connected. They will make you the acid at the end of the day. So just some examples. You have some random ester. So carbon-oxygen bond is broken. So then you are going to take your leftover parts and connect it to the OH from the water. You make an acid, right? So then you have your O ethyl with an H. If you cap this oxygen with a hydrogen, then you will just obtain the alcohol or ethanol in this case. So yeah, I think at this point, actually, we are going to stop our chapter. So, well, maybe like one more thing that could happen, right? So that's going to be just an interesting example. You can also have the basic hydrolysis, right? So this will be different because you're just going to use the inorganic base, such as sodium hydroxide. So the products will be a little bit different here. So, but what's going to happen is the following. You are going to obtain apparently the carboxylic acid salt, right? So because you have the sodium plus ion here, then you are going to make an acid, and then this will become a salt immediately upon the reaction completion, right? So here we just need to look at the building blocks again. So yeah, basically, so here you have it, right? So let's try to draw here for convenience. I'm gonna choose maybe, okay, so we have our ester. So apparently, so this kind of like R prime O part will be eliminated, right? So then kind of counterintuitively, the hydroxide. So it will just eliminate letter H. Let's put it this way, right? So the mechanism, how this actually happens is like more complicated, but for our things, we're going to simplify stuff, right? And then this will look a little bit incorrect. So, but we will get the correct products. So that's what matters for now. So now these are your building blocks, right? You'll need to connect the parts which are red. And then here, if you kind of like put together what makes sense, it's going to be looking like as ROH, right? So that's going to be your alcohol. So these are your red parts connected. Okay, so now the leftover parts will be maybe in green, for example. And now, according to your previous homeworks, you are going to see that it's going to be your RCO, O sodium, right? So that's the one. So you are going to obtain the salt of the carboxylic acid with its respective charges, right? So these are your green parts connected like so. So again, like fair warning, just kind of like don't put oxygen like anywhere else. Well, maybe some people will try to attach this kind of like light blue oxygen to the R group somehow, right? So no, it's not gonna work. So you need to like see, like there's only like one way basically, right? So that kind of makes things easier, but you need to like know it. So then again, some examples. So here you go, right? So I'm going to just like use the exactly same pattern. So H, and then this one, right? So red parts will give me alcohol, and then that's what the alcohol is, right? So then the green parts are supposed to give me the salt. So that's 1 and 2. And I have CO sodium. So that's the one, right? So I have my CO sodium. So sodium with a plus, oxygen with a minus, so which is again what we saw in our salts of carboxylic acids, right? When we were just like making the reaction possible between the acid of some sort, carboxylic acid, and sodium hydroxide, right? So that was shown by Lucas, by the way, back in the day. So yeah, now let's see what we have. So now we can, I think, move on. So here is the question. So do we want more of the ester reactions or do we want amines for the remainder of 15 minutes? Ester, okay, great. So that people have spoken. Let's do more esters. So here is going to be just example reactions, to be honest, right? So in which case we are going to apply what we have just seen. So let's take a look. So here we go. So yeah, basically these are all hydrolysis examples, right? And then you can see the pattern here. We have A, B, C, D, A and C. So these are all ester hydrolysis with the base. B and D, these are all ester hydrolysis with an acid, right? So let's do one of each, I would say, at least, and see what happens, right? So first of all, we are going to take a look at, let's do A, right? So here we go. So we have the ester plus base in water. What's that? So this combination of factors gives us or leads us to the hydrolysis, right? So I'm going to do my kind of like circling, right? So we'll need to make the alcohol H and this kind of like isopropyl with oxygen, right? So they will be connected. They will make you isopropanol, which you can find at the pharmacy, right? That's going to be your product number 1. So OH. Okay, isopropyl, oxygen H, right? So isopropanol or 2-propanol, right? So that's the alcohol product. So now the other one will be the salt, apparently, right? So according to, again, general example. So it's going to be this guy in, blue, and this one in blue. Okay, great. So let's put them together as well and see what happens. So we have the aromatic ring here. Okay, so that's a little bit ugly, but looks like it's working out. So carbonyl, then we have O sodium, right? Sodium is supposed to have plus, and then we have oxygen with negative sign. right next to sodium, right? So and then you can explain why this is the case if you know what acids are, right? So especially carboxylic acids in these circumstances. So now let's take, that was the base hydrolysis. Honestly, this will be exactly the same situation, except with new structures, right? So, and then I can just circle what kind of alcohol you are going to get. So that's going to be your alcohol. So if you connect the parts in red, you are going to get methanol, right? And then you'll have the respective carboxylic acid salt. So yeah, maybe it's going to be looking like this. So not maybe, but for sure, rather. So let's show it. So that's your salt, right? So, and then the methanol will be CH3OH. Okay, the first alcohol ever. So now let's take a look at the acid-assisted hydrolysis, right? So you still have hydrolysis here, so like with the water. So, and then you have H plus as your conditions. So you have the ester. So this should kind of like lead you to the fact that we have acid-assisted or acid-catalyzed hydrolysis of the ester, right? So what are we going to make there? So yeah, basically, so what's going to happen is that you are going to make the alcohol and the acid, right? So this bond will be broken, and now you are going to make your acid, right? Let's see, to the left of the like yellow line, yellow squiggly line, you are going to have your acid part, right? So which is going to be like this. So carbonyl, and now I just need to have OH, which presumably comes from water, right? So now if water gives like OH part, right, in this reaction, kind of as a building block, right? Not that water donates OH minus all the time, right? So it can do both actually. So, but for now, we just say like water gives OH in this specific reaction, right? So as a building block. So now we'll have also H left over from the water, and we have the right side here, right side in relation to the yellow line, okay? So what's going to happen? So let's connect them together. So it's going to be O with isopropyl, and it's going to be connected. Oxygen will have the bond to the H from water. Let's underscore it, right? So as you see, H underscore OH underscore becomes H2O. So that was our water. And leftover parts will be nothing more than your original ester, right? So if you just kind of like look at the balancing, good old balancing, then you'll be fine here. So this is going to be just your catalyst, right? So that's something that will accelerate the reaction process, catalyst. Okay, so now ultimate examples, since you wanted that. So what's going to happen here, right? So I'm going to show the squiggle line like so, right? And now you can see that downwards you will have your alcoholic part, which is almost an alcohol but without H. And it's going to be like upwards, you'll have your acidic part, which is almost the acid, but it just misses the OH group necessary for the carboxylic acids. So let's remove this deficiency, so to say, and see what we are going to get, right? So that's almost an acid. So, but now this is looking good, bless you. So then next one, let's draw our almost alcohol, right? So which is like this, oxygen. What's missing? You need to have H, right? So, and then this is your bond. Okay, great. So these are our examples, and this is just some conceptual scheme, and you have the cat, right? So now let's switch gears a little bit. So because we started talking about the bases at the beginning in the morning, so like we'll continue talking about them as well. So previously, so you had, I'm gonna like get some kind of like examples here, like which are kind of like important for amines. So in terms of amines, so what do we need to have, right? So let's actually take a look at them, like take a look at the new chapter, right? Which is gonna be chapter 16, part 1. And here we go, right? So for amines, you will have different examples. But basically, let's start with NH3, right? So which used to be this guy, right? So it is ammonia with a lone pair of electrons. So somehow the chemical transformation happens, right? And now you are going to switch one of the hydrogens. It kind of brings us back to exam number 1, right? So we were like thinking about how to switch some atoms and then substitute them with other groups of atoms, right? So here, exactly what happens, right? So from this like very simplified perspective, so now you are going to eliminate this third hydrogen and switch it to something organic, such as maybe it's going to be, let's make, for example, propyl, right? So now you have CH2, CH2, and CH3. So that's it. That's your first example of the amine, right? So this is going to be your switch, right? You switched from the hydrogen atom, small atom, to this like huge alkyl chain from alkane, basically, and now you have your amine. That's it, right? So that's kind of the first thing. And now we'll be like later on complicating things, right? So we'll like basically make more switches. All the hydrogens were eliminated. Now each hydrogen was stopped with a methyl group, right? So like quite exciting. So now let's take a look at the base properties, right? That's kind of like the first pretty much chemical property of the amine, which you can think about, right? So I'm going to show another crazy amine, which will be like this one, right? So it will have the aromatic chain or aromatic ring, but no big deal. So then we'll have some sort of chain of 3 carbons. Finally, you'll have your NH2, right? So that's your complicated organic amine. So they can act as bases. So let's show how this will react with water, HOH. As we remember, so water can be used as an acid, right? Which in this case is going to be an acid. So amines are bases, right? So this is our base situation. Now you can predict the products of this chemical reaction, right? So it could be like a nice bonus point question for the exam. Just saying, so you can gain some points, right? We'll see who comes on top in this case, right? So you have your N, so H is here. So now this bond is broken, right? So hydrogen, water will lose H plus and OH minus will be formed as well. So let's just leave OH minus alone, right? So I'll just tell you that. So that's going to be the water byproduct. So next, you will have the bond, right? So here are your green electrons, which are now shared, according to one of your peer who literally said the nitrogen will lose an electron. So it will lose an electron. It lost one of the green electrons, right? So water lost H plus. So this is your H plus from the water. And now it's going to be here, right? So, but at this point, at the product side, H plus gained the electron, this green electron. The green electron came to H plus, right? So, and now you are going to have your H with a dot, which is nothing more than just a hydrogen atom. So you are going to make the bond. Okay, and now the only thing that's missing is the positive charge on the nitrogen. So that's it. That's kind of like how your amines can behave as bases. So that's going to be just like again, it's the same as NH3, right? That can react with water as well. So except you have modified NH3. One of the hydrogen was eliminated, right? And switched to this guy to make your amine from ammonia. So yeah, that's going to be our closing thought, so to speak. And now we will maybe get to the exit ticket. We have like a couple minutes technically, so I'm going to launch the exit ticket in your what's that? Exit. So how did we do, right? So yeah, I'm asking this question now. You're welcome to answer that. And then we are going to stop the recording. Bye, everyone.